So for this problem, we have a tank. It sounds like it's rectangular. Do my best. Not very good at drawing. I don't know. No, that's not right. You get the idea. It's a rectangle, right? It's got a rectangular base and it's a three-dimensional object. Okay, so that tank has a rectangle on the bottom. We're supposed to find the pressure on that bottom of the tank. So force, in this case, is the force of gravity and weight of that water pushing down on it. So force is pressure. Force is the pressure on the bottom of the tank times the area of the bottom of that tank. So let's see. The force of the water is the volume of the water times the density of that water, the 62.5. And so since it's a rectangle, the volume is just length times width times height. 2 times 5 times 3. So it makes 30. 30 for volume. And then times 62.5 for density. So that's 1,875 for force. And so if you plug that into our formula for the equation of force, pressure, and area, actually, so that's the answer. It looks like that's the answer for part 2. On the bottom of the tank, it's 1,875 pounds of force on the bottom of the tank. And then if you plug that in for F, for force, then that's equal to the pressure, which we still don't know, times the area of that bottom of the tank. Remember, it's a rectangle. So the tank has a height of 2, and that means it's 5 feet long and 3 feet wide. I didn't draw that rectangle correctly, but 5 times 3 makes 15 for the area of the bottom. So if you divide 15 from both sides, the pressure on the bottom of that tank is 125 pounds per square foot because it's two-dimensional. So 125 is our answer for A, 1,875 for B, and then for C, it's asked us to find the hydrostatic force on one of the narrow sides of the tank. So I think I really do need to make that drawing. Because one of the narrow sides of the tank, so one of the smaller sides. I mean, I can draw a cube. Shouldn't I be able to draw a rectangle? I mean, it could be better. But it could be worse. Go further. I'm sure it's painful to watch this video if you know how to do this drawing. I think I got it. That's not bad. Okay, there's our tank. So a narrow side is trying to say that it's the smallest side. This has a height of 2, a length of 5, and a width of 3. So this would be the narrow side, right? Because it has an area of 6 square feet. This one would have an area of 15 square feet. And we're not talking about the bases. We're only talking about the sides. So I assume that's what they mean. Narrow, yeah, because 3, that's pretty short on this side. So we want to know the pressure. We want to know the force on this side. So our textbook does a similar problem where the force on the wall is the density. In this case, it's water multiplied by the width of the object times the height of the object. So the width of the side and the height of the side. So the force is going to be, we're going to integrate from 0 to 2. I guess it's the only way that makes sense because water, once you start pouring it in, it automatically fills up the entire width. Our width doesn't change because it's a rectangular base. If it was like a triangle trough, then the width would be changing. We need to come up with a function with it. But the width is constantly 3 here. 62.5 for the density of water. The width is not a variable. It doesn't fluctuate. It's just 3. The height does change over time. Right here, the height is a certain it's a certain height, it's a certain distance off from the ground. Here it's a different distance. Here it's a different distance. The height goes from 0 to 2. So if you wanted to do it, you could do this without calculus, but that would be calculus setup. 62.5 times 3, 187.5. And then the antiderivative of h is just h squared. Evaluate that from 0 to 2. And if you plug in 2 squared is 4. 4 divided by 2 is 2. 2 times 187.5 is 375 for our force in pounds on the side of the wall.